Hello everyone, I'm Zsófia Talyigás, a PhD student at the University of Bath, and I work with Sarah Pennington and Matt Roberts. In this video, I will talk about our result on genealogy of the n-particle branching random walk with polynomial tails. So let's see first how the n-particle branching random walk works. I will write N-BRW for the name of the process. So the N-BRW is a discrete time particle system with n particles on the real line at all times. It's an iteration of branching and selection steps. So first, what is branching? Well, first, each of the n particles is replaced by its two offspring. Then each of the two n offspring particles performs a jump from its parent's location according to a given jump distribution. And these jumps are independent, identically distributed, and non-negative. So children move away from their parents to the right on the real line. And then after these jumps comes the selection step, where from the two n offspring particles, only the n rightmost particles survive and they form the next generation. So here's a little example with n equals to 2. So let's say we've got these two particles at some time k, and, and then after a branching step, they have altogether 4 offspring particles. But with the red circle, I indicate that the two particles on the left don't survive the selection step, so only the two rightmost particles will be in the k plus first generation. Okay, so this is how the N-BRW works. And now here's some notation. The ordered positions of the n particles at time k are denoted by x1k, x2k, and so on, xnk. And I will sometimes refer to the n particles on the real line as the particle cloud. Okay. Now, one of the motivations to study the N-BRW is that it's a toy model for an evolving population under natural selection. So we can think of the locations of the particles as fitness levels of individuals in a population, and then we are saying that only the fittest individuals survive and have descendants in future generations. So this is one motivation. But also purely from a mathematical point of view, this is an exciting model to investigate. And one of the reasons is that the N-BRW shows very, very different behaviors with different jump distributions. So now I will talk about some important previous results on the speed at which the particle cloud is moving to the right on the real line. In cases of different jump distributions. So let's recall that x and k denotes the position of the rightmost particle at time k. And then assuming that the jump distribution has finite mean, we have a deterministic asymptotic speed as time goes to infinity. So we can take the limit as k goes to infinity, x and k over k, and then this limit exists almost surely end in L1, and it will depend on the jump distribution and on the number of particles n. So I will write Vn for this limit for this asymptotic speed, and I will now mention 2 previous results on the behavior of Vn as n goes to infinity. So the more recent result is about a heavy-tailed case of the N-BRW, where the probability that the jump is greater than x is about x to the minus alpha for large values of x and for some fixed positive alpha. And in this heavy-tailed case, the asymptotic speed Vn goes like a constant depending on alpha times n to the 1 over alpha times log n to the 1 over alpha minus 1 as n goes to infinity. So in particular, this means that the asymptotic speed Vn diverges as the number of particles n goes to infinity. And this is a result from Barrar and Meyer from 2014. And now in contrast, we can look at the light-tailed case, by which I mean that the jump distribution has exponential moments. And in this light-tailed case, the asymptotic speed Vn converges to a finite limiting speed V infinity as n goes to infinity. And the convergence rate is very slow. So V infinity minus Vn goes like a constant times log n to the minus 2. And this result was proved by Barrar and Guret in 2010, and it was predicted in the physics literature by Bruni and Derrida in 1997. So this finite limiting speed in the light-tailed case is a very, very different behavior from the one in the heavy-tailed case, where, as I said, the asymptotic speed diverges as n goes to infinity. Okay, so these were some important previous results. And now I will turn to our result, which was predicted by Berrar and Mayer. And so our result is about the heavy-tailed case of the N-BRW, and it describes the long-term behavior of the genealogy of the population for large n, for large number of particles. And since the jump distribution is heavy-tailed, the key idea will be that the long-term behavior of the N-BRW is governed by extremely large jumps, which I will sometimes call big jumps. So now, before I state our result, let's see why these big jumps are so important in the N-BRW. So let's see what happens when a particle like this green particle makes an extremely large jump and gets far ahead of everyone else in the population. Well, then the descendants of this green particle have a big advantage compared to the descendants of these other particles at the back. So they have a good chance to survive the selection steps in future generations. And in my example, they eventually take over the whole population. And since the number of green particles doubled at each time step, they needed log base to n time steps to take over the whole population of n particles. So this is just an example. This is certainly not not exactly how the typical behavior of the N-BRW looks like for large n. But this is a very important idea to start with. And it also kind of suggests that in the genealogy, the time to coalescence should be of order log n. And now I will state our result, and we will see that this is indeed the case. So here's our main result. This is a slightly informal version of the theorem we've proved, and here it goes. For all integer times t with t greater than 4 log 2n, if the jump distribution in the N-BRW has polynomial tails, then with high probability at time t, the genealogy of a sample from the population on a log 2n timescale is asymptotically given by a star-shaped coalescent, and the time to coalescence is between log 2n and 2 log 2n. And on with high probability, I mean that with probability converging to 1 as n goes to infinity. So now I will explain this result a little bit further, and I will clarify what I mean by star-shaped coalescent on a log 2n timescale. So we're gonna look at this figure. In the figure, Ln stands for the ceiling of log 2n, and epsilon n is a sequence in n which tends to 0, but with epsilon n ln going to infinity as n goes to infinity. And now in the figure, time increases from bottom to top, and little t is an arbitrary large time. So now imagine that the population is huge, so n is very large, and we pick a small sample from this huge population. Let's say we pick 6 particles. Then these vertical lines represent the ancestral lineages of the sampled particles, and we merge 2 lines into one, like here, when the 2 particles corresponding to the lines have a common ancestor for the first time, going backwards from time little t. So this is how the picture works. And then now the first main message of our genealogy result says that there exists a random time, big T, in the time interval little t minus 2 log 2n, little t minus log 2n, such that with high probability, if we take a uniform sample of m particles from the population at time t, in the figure we took 6 particles, then the leader at time big T is a common ancestor of the m particles. And on leader, I mean the rightmost particle at time big T. So this is what we see here, that going backwards from time little t, all the ancestral lineages merge into one by time big T. So there must be a common ancestor of everyone in the sample at time big T. Now, the second message of our genealogy result says that all coalescences of the lineages of the m particles happen within a time window of size little ordo Ln. So this is what I'm illustrating here, that all the coalescences occur in this little time window. And this means that if I look at this picture on a log2n timescale, then all the coalescences will appear to happen at the same time. And this is what I mean by star-shaped coalescent on a log2n timescale, that all the ancestral lineages merge into one, and they merge into one basically at the same time, looking on the log2n timescale. So this is what we proved. This is our main result. And then let's see how this compares with the light-tailed case. Well, it's supposed to be quite different. The conjecture by Brindley and Derrida says that the genealogy in this case should be given by the Bolthausen-Smithman coalescence rather than a star-shaped one. And the time to coalescence should be of order log n cubed rather than log n. So here we see some, again, some very different behaviors in these two different cases with these two different jump distributions. And now I will finish off with a little video in which I simulated the N-BRW with 3 different jump distributions. So I've got a heavy-tailed or polynomial jump distribution in red, a light-tailed or exponential one in blue, and a stretched exponential jump distribution in yellow. So this is sort of an intermediate case between the other two. And let's see how it goes. So if we look at the red particles, then we see that sometimes there is a particle like this one, which jumps far ahead of everyone else, and then the population sort of catches up with that particle later on. And if you look at the blue particles, then they are just peacefully moved together. Nobody makes an extremely large jump. Then the video repeats itself a few times. In case of the yellow particles, they are doing something in between the other two cases. There are many open questions about the stretched exponential case, and this is what we are currently working on. And this is what I wanted to say. This is the archive link for our paper, and that's all. Thank you for listening.